Our next speaker will join us virtually or join us online. I hope, we can see you. So Dr. Christophe Lasseur from the European Space Agency is a project manager of MELISA project, which stands for Microecological Life Support System Alternative. Dr. Lasseur acts as European representative of the ISS Medical Board for Microbiology and also serves as an advisor for several European Union activities. The topic of the next talk is Mars Transit Habitat as an example of circular economy. So I would say the floor is yours. Thank you.
Thank you. Thank you very much for this invitation and the opportunity to talk in a nice place, which I don't know, but I have heard a lot, and certainly a famous place for the number of Nobel Prize, specifically in chemistry. So when we talk about Mars transit or Mars mission in Europe, for a lot of us, and at least for my generation, it's a dream which is postponed, I would say, almost every year to a date that probably nobody will see or nobody thought we could see. But very recently, in fact, if you look at the September this year, during one of the ESA official meeting, ESA proposed to the European country to seriously consider the Mars transit mission. Yeah, and this Mars transit mission will be, let's say, probably with a very strong expertise in what we call the life support domain, with the capacity to have a European position in what we call the life support, and I will have the opportunity to explain it to you, starting most probably by what we call a ground analog in order indeed to be able to validate. So we are not anymore in a kind of a dream, but really entering very seriously in the European position of a Mars transit collaboration. So any astronaut or any human to survive in space needs a minimum of metabolic consumable. Of course, we are all thinking about oxygen, then comes water and food. We have a tendency to forget as well all the waste which are produced more or less at the same equivalent of mass. Even some of them which are very low in mass, such as the microbial contaminant or the physical contaminant, are accumulated in a very small vehicle and can become dangerous for the mission. So if we do a bit of a basic calculation, you probably know that a human more or less consumes 5 kilos of oxygen, water, and food per day. For a mission of 6 people to Mars, we're going to be around 30 tons. And if you add a bit of water for hygiene quality, 3 years without any hygiene is probably a serious difficulty, so a bit of water. And if you put at the top of it the packaging, the tissue, and so on, you are in mass which are clearly absolutely not compatible with the current launcher, and even not with the SLS, who is not today able to carry such a mass. So clearly there is an issue here. Something that people doesn't realize very often is that space vehicles are very tiny. They are, first of all, extremely airtight because outside is vacuum. And they are very tiny as well because they have to be launched and they have to be set up at the top of the rocket. So the volume is quite small. And if you compare the human density on board space vehicle, or at least on board the International Space Station, one compare to well-known cities in the world, you see that the human density is extremely large. What does it mean? It means that the risk is much higher and will accumulate due mainly to the human activity. Yeah. So today, how do we do? Today, the space station is orbiting around the Earth, around 400, 500 kilometers. So we have the capacity to regularly, every 3 to 4 months, to send some cargo who transport the oxygen, water, and food, and the waste are burned in re-entry. But as soon as you quit the Earth's orbit, this is not possible anymore, and you really have to move to something different and try to recycle as much as possible on board the space vehicle. So, of course, there is not one technology who take the waste and transform them in oxygen, water, and food. So how do you select this technology, or do you assemble them to have the highest degree of recycling, and of course the highest level of safety, keeping in mind that we want to bring back our astronaut healthy. So in Europe, we use what we call the ALICE criteria, which is a multi-parameter tool, in order to be able to compare subsystem and system with this spider graph. We don't do the selection for the project manager, but we give information. So of course, the efficiency of recycling is extremely important. The mass of the hardware, if the hardware is higher than the consumable, better not transport the hardware, transport the consumable directly. The energy, the safety, and the crew time. So in Europe, the project which is the most, let's say, active is this domain is called MELISA. You probably have heard about it. It's a project which has been initiated roughly 34 years ago. It's only start coming from Airbus. It's only start with mainly 2 countries, and now it's involved 12 countries and roughly 45 organizations. It's a reasonable size in terms of manpower resources. We are around 100 people active in MELISA. Very multidisciplinary background. We have, of course, quite a large number of chemical engineers, but we have as well microbiologists. We have mathematical model experts, software engineer, safety engineer, medical doctor, cooks, and so on. Yeah. We welcome as well PhD quite regularly. To give you an idea, there is around 20 to 25 universities involved in MELISA. And this one is maybe known from you because she's come from Poland, and she was 2 years with us in ESA, here in the technical center, Johanna Kusma, and she now starts a PhD in the French university. Yeah? So, roughly 30 years ago, the scientists and the engineers thought, how can we transform the waste in oxygen, water, and food? And they realized that at least there is a system which exists, was at that time probably the only one, is a terrestrial ecosystem. Yeah? But of course, we cannot fly a lake. It's far too complex. It's not understandable. It's too heavy. It's too bulky. And the complexity of it was not at the level of understanding at least 30 years ago. But the function of the ecosystem are here and should allow to be able to transform the waste in oxygen, water, and food. And as engineers do, when they don't understand something, they like to cut it in smaller pieces and try to understand these smaller pieces. And if they work, then they should be able to have a complex system. And this is exactly what they have done here with the lake. They consider that there is 4 functions in the lake, starting from the bottom part of the lake with the waste, going up to the photosynthetic process, who will be there to produce oxygen, water, and food. So here, another vision, much more oriented chemistry. You have 3 processes to transform the waste, and 1 process, what we call often compartment 4, to be able to produce the oxygen, water, and food. So clearly, you see very rapidly that such a system is totally unstable and becomes stable and efficient if you are able to master the flow between the different processes. This is why MELISA is characterized by a very intensive, let's say, engineering approach. We try to characterize all the process at a very level of detail, and we have here another view of a closed system. Yeah? So there is quite a large number of challenges in front of us. Of course, the circularity. What you produce is becoming your substrate. You have to demonstrate the efficiency of all the sub-processes. It has to work in static and dynamic mode, otherwise you will need big buffer and big mass. You need to model and control biological processes. 30 years ago, it looks like a very big challenge. Of course, we have done a lot of progress these days. You cannot limit your thinking to carbon and nitrogen. You really have to go broader. And of course, it has to be properly controlled in terms of safety and acceptance. Something which is important, because when we start MELISA, it was really the early day of Europe, is to be able as well to have this international community around the table for a large number of years and to convince that there is an interest to study something which was, as I said at the beginning of my talk, postponed almost every year. Nobody seriously were considering a Mars mission, at least not a human one, and this is changing quite rapidly these days. Yeah? So, how do we do? So we're gonna characterize all the processes in terms of biology and physical parameters to be able really to have mathematical equation representative. We are not speaking about fitting there, we are really speaking about mechanistic model in order to really have the maximum of behavior information. Keep in mind that today we have no hardware on board the space vehicle who could be the Mars Transit Habitat. So anything related to data collection or big data management will not work, and it will be post-mortem, if I may say. Now, as you are working with a circular system, you have to be able to predict and not collect the data after the processes. So we do that with all the processes, and I take the example of plants, which are, of course, one of the most complicated ones, with a large number of input flux, either from the root, either from the leaf, and as well output flux, and different type of cells, different type of biomass quality coming from the straw, going to the edible biomass, and so on. Yeah? It is not enough to be able to produce proper biomass. You need as well to be sure that it will be accepted. And when you are in microgravity, there is a very strong fluid shift of the astronaut body. What does it mean? It means that the main part of the liquid will, let's say, be reorganized in the upper part of the body. And this means that the astronaut will have a different perception of taste for sugar, salt, fiber, and so on. So it's important as well to be able to characterize these recipes in, let's say, more realistic conditions. So we do that generally what we call bed rests, which are organized by the European Space Agency, either in MEDES in France, in Toulouse, either in La Charité in Berlin, where we have volunteers during weeks, sometimes during months, as this one, who are head down in order to simulate this microgravity. And it's, of course, an opportunity for us. So clearly, you see that technology here is very linked with human physiology. The interface between life support and human physiology is, of course, extremely important. Things that you have to realize as well, that you'll never have the diversity of food that you will have on Earth. On Earth, we are eating sherry in January and so on. If you go to a space mission and if you would have the same qualities than on Earth, you will need somewhere around 800 square meters per person. So it's, of course, not compatible. This is why we are more thinking to cultivate around 8 plants and to challenge the different opportunity we will have in terms of food. Something that you have to realize as well, you will be in a very harsh environment. You will be on the other side of the Van Allen belts, exposed to radiation coming from deep space or coming from the sun. And this means you really have to be able to detect the effect of the radiation, harsh environment, on the different steps of biological processes. Don't forget that we cannot avoid biological processes because we want to produce food, and today we are not able to produce food, even artificial meat, without going to biological processes. For those who are experts in electronics, they know as well that radiation has a very strong effect on the electronic board as well. Yeah. So how do we do that? We normally start at the university, academic world, where we characterize the process for a few weeks, a few months. Then we go to something much bigger, much more engineering oriented, such as the same function here, but you see a lot of sensor, a lot of instrument. And once it's done, we are able to scale it down as this one, this very little sugar box, if I may say, who flow on board the International Space Station to validate our process are properly characterized. And then we are able to do the exercise of scaling up in order to be able already to see how we position ourselves for this Mars transit habitat. So access to space is, of course, very important. Just would like to mention the Artemis experiment is one of the 10th Melissa experiments who flew on board ISS or on board Bion when we collaborate with our Russian colleagues. This one was to validate the production of oxygen and as well production of edible biomass. So we demonstrate that we are able to predict. You could see on the right-hand side the graph of the mathematical prediction, which is more or less a copy of what we were able to measure during the space mission. So it was a mission of roughly 6 weeks with 4 processes. So we really have a duplicate. So it's not by chance that we obtain this result. And here we are able to show the oxygen production as well as the biomass production as a precursor of what we could do later on. We will never do such a mission without a ground demonstration, and I know that in Poland you are as well involved in this kind of activity, especially with the LUNARES project. The main part of the activity of Melissa are focused in terms of integration on the Melissa pilot plant, which is located in Spain, which is a high clean room location where we are able to progressively assemble the different processes to reach the highest degree of closure. So what we have done very recently is this one. We inject, to simplify to our processes, CO2 and urine, and we demonstrate that a very high control of the two processes that we have, we call nitrification for urine treatment and photobioreactor for GLJ, we are able to supply over 18 months the quality of oxygen which is necessary for rat habitat, and the rat habitat, it as airtight as the International Space Station. It totally depends on the mathematical model which are running the process. And with CO2 and urine, we are able to produce oxygen and protein. And if you look at the blue curve, you see that we are really able to maintain a different level of oxygen on the y-axis on the right-hand side, the concentration we say selected by the operator, moving from 21% to 19%. So it's really a very good demonstration of stability. So all this work is indeed done for probably a crew of, I would say, 5 to 6 astronauts, and some people may wonder why we are spending so much effort and so much energy for, and so much budget as well, for only these 5 to 6 volunteers. So we are very pleased as well to realize that Melissa has a strong impact on terrestrial market, either in the agro-food, the life science, or the waste and water issues. And I would like to give you a few examples. So here an example of Concordia, which is an Antarctic base, where we have a water recycling unit for more than 10 years, which is, let's say, able to recycle shower, dishwasher, washing machine water at a very high level, and that's totally dependent of this technology. This Concordia station is extremely isolated, only accessible during summer, so it has to be extremely robust. We are pleased as well to recycle all the shower water in Roland Garros. If my memory is correct, Poland has as well some very good results in Roland Garros over the last years. So just a clin d'œil, as we say in French. We have Kenitra in Morocco, where we recycle water from the University of Kenitra. It's a small university, but we are able to, using as well sun energy to recycle water for this university. We are speaking here about potable water. We have the e-drone technology, which is today demonstrated in the city of Ghent in Belgium, where we treat urine with a specific technology, which is patented, authorizing us to recover on one side fertilizer, water, and on the other side, a biocide, in order to be sure that the toilets are properly disinfected and avoid to spread as well potential viruses as all the world is facing these days. Yeah. In construction in Paris, in the south part of Paris, close to Bibliothèque François Mitterrand, who know a little bit Paris, this green building by the company XTU, which is colonized by microalgae on the south side, in order to produce biomass of high value, but as well to indeed improve a little bit the carbon balance of the building. So this building should be open in 2023, roughly a year before the Olympic Games. EasyCall is one of the 6 Melissa spin-off company. This one is quite interesting because we discover that one microorganism that we wanted to use for waste recycling has a very strong effect as well on the bad cholesterol. You see, speaking about 1 gram per day, we are able to drop the bad cholesterol of roughly 15%. So we took a lot of patents. So we have 15 patents these days. We did human tests, several series of human tests, with all the ethic board and so on. It's quite an exercise. And now we are speaking with some key player of biotechnology and pharmaceutical world in order indeed to stop this activity, or at least to commercialize it, which we, as the European Space Agency, has no desire to enter in the pharmaceutical market. Something that you have to know as well is the MIDAS project. MIDAS project is a team up of the European Space Agency with a world leader of microbial detection. We have been working for 13 years with this company for the automatic detection of pathogen on board the space station. And this allows this company to have a unique technology. Once the COVID-19 appears, there is 3 factories worldwide which are producing this biofire. And the core of the research, the core of the technology, which is named PCR, and everybody knows PCR, but it was a fully automatic PCR. And in 1998, when we start this, it was not that known as it is today. So a clear example of space impacts on your daily life. We as well realize that some people in some countries are a bit less lucky that we are in Europe, where we indeed have a very good living condition. And some part of the world, they have no protein or low possibility to have protein. And this is why we participate as well with our knowledge to the production of protein with a, let's say, very robust hardware, as you can see, but having the advantage to be able to participate to this diet improvement. Yeah? So, for those who are interested by MELISA project, I would like to mention that for PhD and postdoc, we will organize the MELISA Summer University in May 2022. So it's an opportunity for, let's say, master student, PhD, postdoc, to have 3 years teaching and lecture about MELISA. It's quite international. It's an opportunity as well to meet the other people which are working on MELISA. And in November next year, we will have the MELISA conference in Toulouse, which is a MELISA conference is organized more or less every 2 years. And it's a conference who gather around 300 people worldwide. We have colleagues from NASA, from JAXA in Japan, Russian colleagues as well, and of course, for the main part of the European countries. The call for abstract will be probably issued during spring. So I hope that with this presentation, I demonstrate that MELISA is a solid and well-supported project. Of course, with the Mars transit habitat, the challenges are enormous, but the terrestrial one are enormous as well. We are by nature fully open for international collaboration. I would like to insist that today, Poland is not part of MELISA, but it is not at least our choice. And we are clearly confirmed that the doors are open to discuss the opportunity. And of course, we welcome PhD and postdoc. And I invite you to follow us on the social network. Thank you for your attention.
Okay, can you hear us?
Yes, I can.
Okay, so thank you one more time. And we do have some questions for our participant. And first question is, who and how can get an internship in the MELISA project?
Okay, so there is several possibilities. The first possibility is to answer to the ESA call, such the one which is open now. So you have to look on the ESA website, the opportunity to join as a master student for more or less a period of 6 months. Then we have what we call the young graduate program, which is more for 1 year to 2 years, and the call will be open soon, I think, as well. And then you have as well what we call the research fellow for those who have a PhD. And the last opportunity is to send us via the Melissa Foundation CVs and motivation letters that we will distribute to the Melissa community, and they will take contact with the candidate if they find it relevant.
Okay, and could you please turn off the monitor icon on your screen? Yeah, the middle one. No, the middle one. Yeah, this one. Okay, now we can hear and see you again. And second question. When I was listening to your presentation, I thought that the Melissa project could contribute to solving many of the problems that humanity will face in the next decades. I mean, the increase in average temperature, which will result in problems with drought and reduced food production. Can you comment on this?
Yes, we will participate. I don't say that we will
Just a
solve
moment,
the
can you turn on the camera? Oh yeah, now we can see you. Okay.
Okay, very good. No, I'm not saying we will solve the problem with Melissa, but we will participate. Clearly, you are perfectly correct to mention that there is an issue of water. It's not the only one, but it's one of them. And by having a valorization of the water we use, not only the grey water, but yellow water as well, and to be able to use these nutrients more locally is as well a way to improve the, let's say, the horticulture and the food production. We are as well, with the Melissa processes, able to produce protein without going to meat at high level of percentage in the biomass, which is as well a way to reduce the carbon impact. So there are several possibilities. Probably the most interesting one is a circular design where we are able to assemble processes in order to have a high degree of recycling. And this is not only with, let's say, recycling processes, but as well with what we call industrial ecology, where we will be able to assemble not anymore processes, but production factories, such as is done these days in Kalundborg in Denmark.
Okay, thank you one more time, Dr. Lasseur, for your lecture, and now we are going to switch to Polish.
Thank you very much.